here on the S.
And where we stand?
Behind him.
Like the same.
You stand on the S, and we stand behind him in a triangle. Yeah.
We'll make it there.
Yeah? Then at a certain moment you can take your diploma from the motor and then you
Come
step
back.
you come back, and let me see. Well, the rest I don't have time to explain. So
We should also
you
go
will
for
see. You can change. Yeah, I'll show you the dressing.
Yeah, sure.
Take care, man.
Okay, hello everyone. Thank you for joining for the public defense, for my public defense, either online or by physically. So in this presentation, actually, I will present my research work that I did during past 4 years of my life, during my PhD, and I will try to present as simple and as short as possible so that you don't get bored too much. You just get the flavor of it, and then we go for the real big thing. Okay, so let's move on. Okay, so the idea of my research is that in normal or in the current practice, you have, this is the kind of current situation, or in the present situation, that you allow some safe distance between the bottom of the ship and the top surface of the mud layer so that the ships can pass through in the port channels. But now the problem is that if you have a lot of fluid mud in the top layer of the sediments, which is very weak, so the problem is that if you maintain this small distance, what will happen that you will create a lot of internal waves in the mud layers. Or to avoid these internal waves in the mud layer, you need to dredge it a lot. So you have to maintain this this distance quite a lot. So then it becomes very costly. So the other solution is that maybe what you can do, you can allow the ships to pass through the top layer of the mud, which is very weak, or which we call it fluid mud. So that's the idea that, okay, if the ships can pass through fluid mud, maybe we can save a lot of money. But then the question is that then maybe we need the rheological properties of that top layer of the mud, or maybe the whole mud bed, because then we can really see that, okay, ships can pass through it or not, or if there is a particular limit of strength of the mud beyond which the ships cannot pass through it. So that's the idea. And typically, this is done by using this density of the mud. So they decide, okay, this is the density value, and beyond that, we need to dredge it. But now we suggest that maybe instead of density, maybe yield stress or rheological properties are more appropriate parameters. So now we are trying to suggest another property, which is important, especially for Port of Hamburg. So that's the main idea of this research. And then here, I try to put some objectives that why we need this study, or what I did in this study. So the first part, or the first bullet point, is actually the main thing that I did during these past 4 years, while the other 3 points are more or less the application of my knowledge. So the first is, so the main thing is that I analyzed the rheological properties of mud as a function of different parameters like organic matter, bulk density, sampling locations, sampling time. So there were a lot of parameters to characterize fully the mud in the Port of Hamburg. So that was the main idea. But where this knowledge will be used, so first thing is that for the CFD simulations, if you want to see how ships can pass through the mud, you need to perform CFD simulations, but then you need the rheological properties of mud for performing that CFD simulations. And then you can also use the data set that I generated during this research for calibrating this in situ device, which is typically used in ports where you can in situ measure the strengths of the sample. So you can calibrate that device with this knowledge. And also at the end, I will try to give a suitable value from where the port authorities can start further experiments in the port by using that particular value of strength or yield stress of the mud. And then I will briefly explain what is rheology. So rheology, I think this is the basic definition, that when you apply certain force on a material, either it deforms or it starts to flow. So that study is basically called rheology. And then what is mud? So basically, you can see here as well, so it's a kind of a quite complex material. So it's a cohesive material, and also have clay, water, silt, sand, biopolymers, so a lot of things. So it's a combination of a lot of things. That's why it's quite complex. And then let's move towards how we collected mud samples. So this is the map of the Port of Hamburg, and these are some selected locations from where we collected the mud samples. And this is actually the device that we used to collect the mud sample, that is called Fromlord. So it's a 1 meter long cylinder. It goes inside of the mud bed, and then it has a lid. So you close the lid, and then you take it out, and then you divide it into different mud layers based on the density, on the visual appearance. So you can really see that it goes from very liquid-like material to a very solid-like material. And then you can really see the effect of density on the mud behavior. And then these are some devices that I used during my PhD to characterize this sample. So I think the most obvious one is rheometer, because it's a rheological analysis. So I used rheometer by using different rheological geometries, but I selected Coet one, which I found it a bit more easier and simpler to use. And then I also used this modified Rheoptica device, which was actually just to see the structure, how it behaves when you apply shear. And then there was also a device to use to analyze the flux when you allow it to settle in the water column. And this device is used to measure the particle size, because particle size can also affect the rheology of the mud a lot. So these were the devices that I used. And now I will try to just briefly explain what I got. I think these are maybe one of the two important results that I got during my PhD. So the one is here, it's two-step yielding behavior that I observed that when you apply shear by using 3 different geometries, I found that your viscosity goes down not in one step, but there is a kind of intermediate step, and then it goes down finally. So what happens that you apply force, and then your mud start to break down, or the structure of the mud broken down. But then I see in the Rheoptica that, okay, there is something happening in the sample that you form these strain structures, which actually gives you the second plateau. So that was the thing, and then we developed this empirical model, Shakeel, to capture this two-step yielding behavior. This Shakeel is nothing but the last names of myself and my 2 supervisors. And then we try to develop this model to capture this two-step yielding behavior. And then from this model, we got this yield stress. And then I try to correlate it with density values, which is the most important correlation that, okay, your density correlates with yield stress, but I also found it also a function of organic matter content. So for Port of Hamburg, density and organic matter content both are important. So that's the main conclusion out of it. And I think that's the major result out of my research is that, okay, if we want to suggest any particular value to the port authorities, that, okay, this is the value of strength or yield stress of the mud, from where that you can start some future experiments by taking the ship out of it, or maybe by putting the ship in the mud and see how it behaves. So we suggested 50 pascals as a yield stress that they can use maybe as a starting point, this value, and then they can do further experiments to further verify it. So it's just a kind of an idea now, but I think it needs further experiments, not maybe rheological experiments, but CFD simulations or validation experiments in the port. So that will be, I think, the final thing that I got from my research. Okay, a lot of lessons. I think it's expected, but I think I'm not going to talk about every lesson. So I think the first one is that we found a nice geometry or nice rheological protocol, that how we can characterize this mud sample, and then we develop a model to capture that particular yield stress behavior, and then we proposed a particular yield stress value. So that's kind of a summarized form of these lessons. Okay, now I think nice part, more pictures. So here you can see some pictures from, apart from my supervisors, I really want to acknowledge people from Port of Hamburg, who actually, I think without them it was not really possible, although from funding point of view, but also from sampling collections, and I think we collected in 22 campaigns. So it was, I can imagine it was a lot of work. So really acknowledging that work, and also our MudNet team. I think a lot of people are already sitting here. I think with most of them I already collaborated during this research, because they are working on maybe in different topics on mud, but at some point we collaborated to have combined research like rheology or biomud and these kind of correlations. And then, people in Deltares, because I spent most of the time in Deltares, so it was a nice journey there because everyone collaborated well and supported well, especially Saskia, because she was like a lab manager, so I think she was helping a lot for making everything possible, especially for rheology lab, and also these other guys. And also there are some students, graduate students and researchers. I think one of them is present here, my master's student. And last but not the least, my wife and little princess, who actually tries her best to make this thesis writing, I think, very difficult. Okay, but I was managed to make it happen in the end. But I think she was quite successful. Okay, in the end, some nice memories during my 4 years of this PhD, going to the boat first time, and after I think when I spent, 8 hours in the boat, and when we came back to our hotel, at the train station, I was like this, and I asked Alex, okay, if I am moving or the platform is moving, and he said, you are moving and you are going to move for 2 more days. I said, okay, that's common then. And then some more pictures from the vessel where we found, I think Florian found this fish, so it was nice that we were catching mud and fish together. And also some interesting flocks, ships, bigger ships, container ships. And then some nice photographs from conferences that I attended during 4 years of my PhD. It was not that much, but still I attended some conferences because Corona came, I think, after my 2 years of PhD. But I was lucky to visit some places at least. The South Africa, yes, South Africa was a bit interesting actually, because I went there for the conference and then it was nice there. And then there was a Interpol conference here in Delft, and I also went to AGU, United States. Okay, this is, I think, the goodbye from penguins. So I think that would be a nice ice on the topic. So let's see what they are going to do for you. Okay, here it comes. Yeah, hello. That was nice journey. Yes, it looks like a PhD journey, that you are coming, but you are stuck somewhere, you look here and there, and then you start, okay, I can go, I can finish it. Yes, you can do it. Yes, I passed the finish line. So that was it. And thank you so much for your attention. I hope you like it and you are not bored.
Ik open de zitting van de commissie ter beoordeling van het proefschrift van Ahmad, Shakeel, Master of Science, Rheology Engineering. De verdediging zal in het Engels plaatsvinden. I request the promovendus to go to the lectern. And his paragraphs. Yeah. A warm welcome to all of you at the defense of the candidate of the thesis entitled Rheological Analysis of Mud Towards an Implementation of the Nautical Bottom Concept in the Port of Hamburg. The Board of Doctorates of Delft University of Technology have installed a committee to evaluate the dissertation as well as the propositions. The committee will have a debate with the candidates in public. I will now introduce the committee members to you. First, we have, in the order of the opposition, we have joining online Professor Manning from the University of Plymouth. Then, here in the Senate Hall, opposite of me, closest to the audience, is Professor Bennemeyer from the University Le Havre. Next to him is Professor Cousseau from University Gustave Eiffel. And next to him is Professor van Loosdrecht from the Faculty of Applied Sciences. Then we move to this table, and at the end of this table, we have the co-promoter, Dr. Kiricek. We have on my left hand, the promoter, Professor Pietrzak, and on my right hand, the promoter, Dr. Chassaigne. All promoters are from the Faculty of Civil Engineering and Geosciences. I thank you all for joining this academic ceremony. My name is Arnold Hemink, and I will share this session on behalf of the Rector Magnificus. It's now time to start the discussion, and I would like to give the word to Professor Manning. Professor Manning, the floor is yours.
It was very nice to meet you. Thank you. I really enjoyed reading it. It's been a great pleasure working with you over the years at Delft. And I'm looking at these very impressive outputs already. We've got 12 journal articles and counted, book chapter, numerous conference presentations. And we really thank you for taking the effort to join our session of the American Students Union board meeting in Washington, D.C. back in 2018. I'd like to start my first question looking at the introduction. But could you quickly explain why populations are more to consider in fluid formation and how it affects rheological properties?
Yeah. Hooggeleerde opponent, yeah, thank you for your nice appreciation and the nice words about my research. Yeah, flocculation is actually quite important, particularly from a rheological point of view, because if you have only clay particles, then the rheology will be totally different, because then you can have only interaction within clay particles, and even if you have like non-swelling clay, let's say kaolinite, then the maybe rheological properties will be very weak, and then it will be only dependent on the solid content, and then you need maybe very high solid content to make it a very strong system or to have a high yield stress values. But when you have, let's say, flocculant or polymer or biopolymer, then you create really flocks, and then what will happen? Then you will create a network of those flocks, or maybe a network structure within the flocks, and that could really change the behavior of your clay system. Because then even at low solid content, with the addition of that biopolymer flocculant, you can create a really strong system, or you can really say that the yield stress of the system will become higher even with the lower clay system or the lower concentrations of the clay. So that's really important, that if you have a flocculation in your system, that going to really change the behavior. And also I think fluid mud formation is mainly affected by this flocculation, because then you have these flocks, and then these flocks can really make a fluffy layer of the fluid And then it actually get problematic because then it forms a huge layer of fluid mud, which is sometimes or most of the time is problematic for, especially for port authorities. So I would say that for rheology and also for maybe navigation through fluid mud or for defining nautical bottom, this flocculation is actually creating a lot of interesting phenomena in the system, both for rheology and both for in situ analysis. So I would say yes, both are significantly affected.
So what do you consider the key factors in terms of affecting population, key factors to be measuring to look at population?
I would say first, of course, the flocculant. What kind of flocculant you have, anionic, cationic, or what kind of biopolymer you have in your system. That will be the first thing that is going to create flocculation in your system. That is the primary one, or maybe the concentration of flocculant. So that will be the one thing. And also then there will be concentration of ions, because that's the another thing that even can create this flocculation effect together with biopolymers or with this flocculant, or maybe without the absence of flocculant, you can even create weak flocks with this kind of salt. So that could be another option. And I think also this solid content also plays a role in flocculation. So that could be 2 or 3 major factors that you need to consider when you are going to see the flocculation or even the effect of flocculation on rheology.
That's fine, that's good, that's great, thank you. So moving on to your method section, I see that you use the flock count to measure particle size distribution. Could you just briefly go over what you think the advantages and limitations of using the flock count and how it compares to other techniques such as satellite scattering?
Yeah, actually I use this flock cam device just to analyze the flocks because it's easier in that system that you can easily analyze. You can track individual flocks coming down, and then you can really see the shape, the size of the flock, and then you can also determine the settling velocity of the flocks. And I think these are quite interesting information, especially for modeling or sediment transport modeling. These information are quite important. So that's why I used it, and I found it easy, but I think there were some limitations, particularly when you try to pick the flocks by using pipette, then you really have to be careful that you don't destroy the flocks, because otherwise if you already destroyed it and you put it in the water column where you are going to analyze it, maybe the flock's structure or the flock size is already changed. So first thing, I think you need to be careful with the pipetting method or the method that you are going to use for putting flocks in your water column in flock cam. And also I think if you have very fluffy flocks or this organic matter, lot of organic matter content, then sometimes it's a bit difficult because you are going to back analyze the videos from the flock cam with some software that you can really see, okay, where is the flock? So sometimes it's really tricky when you have biopolymer or flocculate there to see the sharp edges of the flocks. So sometimes it's get tricky there that you really find the boundary of the flocks, because then you can really see the size or the shape. So sometimes it's get tricky there as well. So I think that's 2 things what I found, because I didn't work too much, because that was one research with collaboration with another PhD student. So that was a kind of a collaboration research that I did rheology, and he was more focused on flocks analysis. And then we tried to come up with a correlation that, okay, how flocks are going to affect rheology. And then we found actually quite nice correlation between these 2 things. Yeah, actually, yeah, I use that device as well for measuring particle size distribution. And I like that device because what I found, it's quite easy to use and quite fast to use. So I think that was the one reason that we're still using for different mud samples. We don't need too much preparation or sample preparation. You just put your big, also 1 drop of sample or even 2 drops of sample, whatever you required, and then you measure the particle size distribution. But there are certain limitations, because for that software or for that device, the software that is using my theory or my assumption theory, which assumes spherical particle. But in our case, we are not having a spherical particle. So that could be one tricky thing, that we are using one software, but the particles are not spherical. So there could be a trade-off. And also, there is a kind of a limitation that you cannot put too much sample in the bucket where you're measuring the sample, because otherwise this laser obstruction, it's got too much and then you don't see anything at all. So you need to put a very small amount of samples. So that's the thing. And also there is one more thing, that if you have like very fine particles and very big particles like sand or very fine clay, then I think this software also sometimes smooth the data to give you D50 value, and I think which is sometimes not the accurate D50 value. So I think these are some limitations of that device which need to be considered.
That's good. That's great. Thank you very much. If you'd like to discuss proposition number 8, please.
Waarde promovendus, could you ask one of your para-nymph to read proposition number 8?
Can you please read proposition number 8 by standing?
When performing a large number of same type of experiments, the most important thing is not to lose motivation.
Could you just briefly explain your experiences with this issue and what do you think other scientists can learn from your experiences?
Yeah, actually, I put this proposition because I think I told to everyone that we did, 22 campaigns for sampling campaigns, and we collected, thousands of samples. And then we were trying to create a database for the rheological analysis and also rheological properties. And I was using the same device, lot of samples. And at one point in the first year, I was really motivated. But then the second year, I need to do the same test maybe again, maybe different samples, but the same test. And then I thought, okay, how I'm going to do the same test again and again and again. And then I thought, okay, I need to remain motivated, because then at the end you are going to create a nice database from which you are going to get a nice trend. But otherwise, if you don't have enough samples or enough data points, the trend doesn't make sense. So then I realized that, okay, maybe that's a big tricky thing, that if you have a lot of samples, lot of same analysis, then you need to be careful that you don't lose motivation and you just keep focus on the bigger objective, that why you are doing this and what you will get out of it. And then I think you can keep yourself a bit motivated. That's what I do.
That's great. Thank you very much. I think I've really enjoyed your insights in this. I'd like to find out how to tell you the laboratory and the scientists can go with that. Director, do I have time for any more questions? That's my time.
Yeah, there's still time for a short question.
Okay, I just want to ask a question about chapter 4, about figure 4.9. If you could just briefly go through what your correlation is with your population data and the correlation you look at in terms of vulnerability properties. If you could just explain what the sort of summary is of that figure, please.
Okay, so yeah, on figure 4.9, actually the idea was here just to plot the settling velocity that we got from flock cam and also the size of the particle. And the idea was just to compare for different locations. So for different locations means we have different organic matter content. So what we did, we have, let's say from A, B, C, D, if you see the top content or organic matter content is in A, it's highest, while if you go to figure D, it's getting lower and lower. And what we found that if you have lower organic matter content, for, let's say, for the figure D, where you have only 2-8%, and for that location, what we observe that it's a huge scatter for the settling velocity and also with this particle size or flock size. So this scatter was actually coming from a lot of sand particles as well. So we were actually trying to measure flocks, but actually we have sand in it. So that's why we observed that, okay, this is a kind of a scatter, but it is not coming from the flocks, but it also coming from some other things, which is actually the sand in this. While if you see the other three, A, B, C, D, there we actually found that, okay, we can estimate the flock density, because we also plotted these isolines with effective density by using Stokes equation. So you can really see that, okay, these are the isolines with different effective density of the flocks, and we can really see that for highest organic matter, it really lies on one value, while if you change the organic matter content, it is shifting from one value to another. So you can really see that the effective density of the flocks that you got from this graph between settling velocity and mean diameter is actually changing from location to location, where you are changing the organic matter content. So that was kind of a main idea that we were getting from this picture.
That's great. Thank you very much. That's good. That concludes my questions. I'm very happy with your answers.
Thank you for the opposition. Then I would now like to invite Professor Benamar.
Dear Director, I have a question about the first proposition.
Waarde promovendus, could you ask one of your para-nymphen to read proposition number 1?
Okay, can you please read proposition number 1, please?
Suitable rheological geometry and measuring protocol are required for analyzing the rheological properties of complex systems like mud.
I would like how you select the geometry, the adequate geometry for your investigation, and how this geometry and the testing protocol can reach the field situation when you investigate the nautical depth.
Okay, how clear the opponent? Yes, actually, while selecting, because when I started my research, there was actually the first obvious question was that, because we have a kind of a complex system, because natural mud is not like only clay or water or clay or biopolymer or water, it has a lot of things in it, and it has like varying density as well, varying organic matter content. So the first idea was, okay, how we can measure appropriately or effectively the rheological properties. So we need to select particular geometry and then also particular protocol to it so that we can do it fastly, because that was one of the goals as well, because we have a lot of samples. So then we tried actually different geometries like coed, vane, or parallel plate. And then the problem with the parallel plate geometry was that, that when you have a very liquid-like samples or very fluid mud with very low densities or very low solid content, and when you try to shear it at certainly higher shear rates, what was happening, actually the fluid or even the particles was coming out of the plate gap. So I thought maybe this geometry is not very suitable for this kind of samples, especially for fluid-like samples. And then I also tried this vane in cup geometry, and that one is actually, I think, typically used as well for mud sediments. But then there is also a debate that, okay, the shear rate that is given by vane is actually not the correct wall shear rate that the software gives. It may be different because the velocity profile is not linear sometimes. So that was actually quite a question for me as well, that maybe should we use it, because then otherwise we need to correct it, or maybe we need to make it a nice comparison with coed or other geometries, but I thought maybe we can avoid it. So I just tried in the end the coed geometry, and it was obvious that, okay, in coed geometry you have linear profile, so you don't have much problem, but in coed geometry you can have some other problems like sedimentation or wall slip. So I also tried rough geometry or with grooves on it just to check if there is a wall slip or not. And then I realized that, okay, with this geometry, I can go for it. And then I also tried different protocols. The one which I selected is stress sweep. And for liquid-like samples, I found out that it took more or less 40 seconds around. So it's a very fast test. So I thought, okay, if even I have a lot of samples, with this time, I think I can do a lot of samples, or I can analyze a lot of samples. And then I also performed some other tests. While with the other test, it was also, you can get similar values, but with some tests, either it was difficult to get the yield stress value, like different criterions, or it was a difficult process, or sometimes it gives you lower yield stress values because you perform a lot of extensive, the damage or the disturbance while performing high shearing action during the protocol. So I thought, okay, maybe for the port authorities, maybe I should measure with the protocol that does not disturb a lot first, but just measure when the sample is in the structured state. So then I thought, okay, maybe stress sweep with coed geometry could be a nice solution for this research where we have a lot of samples. So I need to be quick and effective as well. So that was the idea of selecting these two things together.
Thank you for your answer. My second question is related to degradation of organic matter and which leads to the decrease of field stress. How this can be reached in field?
Yeah, actually, that's important, because that's what the idea, because when you collect your mud samples, maybe it's already there, or maybe it will remain there for a bit longer time. So the idea was that, okay, if the sample is there for a longer time in situ conditions, the organic matter in the system will degrade. And then the question was coming that, okay, how is it going to affect the yield stress or the rheological properties? So first, to confirm this idea, we performed this together, or combined research with biomud. And the idea was that we collect samples, and then we allow it in certain conditions to allow it to degrade. So we measure the rheological properties before degradation, and also I think 250 days of degradation we measure again. And then we found out that there is a huge decrease in yield stresses and also other properties. But then there was another question, that in situ conditions, when you leave the mud for, let's say, 250 days, there are strong possibilities that there will be settling consolidation as well. So what is settling consolidation? That your density is also changing in the system, or it is getting stronger with respect to time. So you leave the sample in the bed, and it is getting stronger and stronger due to settling and consolidation. So there were actually two things which are happening together. Your density is becoming higher for the same sample or for the same layer, and your organic matter is degrading. But this kind of experiment I also did in the lab, where I put some samples in the cups for a long time, just to see how it settles down or how it consolidates, and also allow it to degrade. And then I measured the rheology after consolidation. And what I found, interestingly, that the consolidation effect actually dominates this degradation effect, because the density increase is more stronger than the TOC effect. So that's what I found, that, okay, maybe in situ conditions, if your density is changing, or if it is getting higher, then you need to be careful that maybe this degradation effect may be negligible, or even your strength will become higher. And you will not see this decrease in yield stress because you are changing your density. So then you need to be careful. If your density is constant, then you will expect a decrease in the rheological properties as a function of degradation time. So that's what we found out.
Thank you. Another question, how salinity can affect the rheological measurements and the results?
Yeah, actually I didn't try for Port of Hamburg, because Port of Hamburg is a freshwater port, so we thought maybe we can try to see the effect of salinity on the rheological properties of mud, but maybe it's an extra work. But then what we did try this thing for Port of Rotterdam, because this is more salt water port, so I thought, okay, let's try there. So we got, because I was also involved in those projects, so we got samples from Port of Rotterdam as well, so we just tried to see the effect of salinity. But what I found, that the yield stress values were not significantly affected by changing the salinity, while the viscosity, particularly at low shears, actually was affected by salinity, because when you have these salt concentrations in the system, you can create some network, and actually this network actually gives you some higher viscosity values at low shears, while at high shears, when you broke everything, salt concentrations are not affecting too much. So that's what we found for Port of Rotterdam, but not for Port of Hamburg, because we thought maybe we don't need this analysis.
Last question is, which is the main parameter to define the nautical depth, the yield stress or the structural recovery?
Okay.
Does the structural recovery can define more accurately the nautical depth?
Yes, actually, that's what I actually did, because in my opinion, I think still yield stress will be kind of the main parameter that can be used for nautical bottom applications or sailing through fluid mud. But the question that you said, that maybe the structural recovery could also be important, or maybe more important than yield stress, that's why I tried to make a correlation between yield stress and structural recovery. So what I found, that if you already have a kind of a limit for yield stress value, let's say I said 50 pascals, and even if you see that below 50 pascals, your thixotropy is already quite weak. So you can say that both are interlinked. If you have higher yield stress values, your thixotropic effect will also be quite stronger. And then you need to be careful. But if you already have a limit for yield stress, which is lower, then you will expect that maybe the structure is not very strong, so you will not have a very significant time dependency. You will have something, because you cannot say that it's not thixotropic at all. There will be some thixotropy, but that time will be, I think, easily recoverable even in situ conditions. So I would suggest, if you are going for low yield stress values as a limit, I think yield stress is still the main parameter, while you can easily correlate it with structural recovery at any time.
Thank you.
Are you satisfied with the answers? Thank you for the opposition. Then we continue the discussion with Professor Cousteau.
So, Waarde promovendus, I have a few questions. So the first question will be concerning the yield stress. You focus on the yield stress in all your thesis as the main parameter. But if I consider a boat, and looking at a boat which moves, we would rather consider the viscosity of the mud. So can you discuss this point?
Yes. Hooggeleerde opponent. Yes, actually first, we also thought that maybe only yield stress is the only parameter or the main parameter that we should discuss, or maybe we should find for different locations. But then when we do this two-step yielding model, and then we also got this static yield stress and also fluidic yield stress, but we also got this high shear viscosity. That's where we can say that, okay, that is also important. And we also know that apart from yield stress, the viscosity that we need, because I think in most of this CFD simulations or this modeling, you need both parameters. You need this yield stress, which is actually kind of representing low shear behavior when the system is structured, while this high shear viscosity gives you an idea when the structure is gone, how much viscous is it. So then you can cover both things together. So that's why actually in the model we put this parameter, and later on in the modeling chapter I also discussed this viscosity dependence on yield stress. So I would suggest that only yield stress is not only important. We are going to use actually yield stress together with viscosity as well in our further modeling or further experiments or maybe pilot experiments and also CFD simulations. So the knowledge is there. I think in the thesis I also put all the data related to infinite viscosity as well. Yes.
Okay, but does that mean that in practice you would advise people to test also the viscosity to have all the parameters, or because probably in practice they prefer to have only one parameter? So,
but I will prefer to have both, because at some point, that's what I just mentioned, that yield stress can give you idea when there is still some structure. But when you have like infinite viscosity at very high shear rate, which means you destroyed every structure in the system, and now you have maybe clay particles or maybe clay or biopolymers or clay or organic matter in some individual entities, but then it can still offer you some resistance due to the patterns of particles. So then I would say that yield stress is important when you are going from, let's say, low shear conditions, because then maybe your mud is too structured, and then you need to overcome this yield stress first. But then if you are already breaking the structure is already gone in the situ, in situ conditions, then maybe the other thing that is important now, because yield stress cannot give you that information now because you already overcome the yield stress. Now you are talking about more viscosity of the system. So I would suggest that if you are going to very high shear rates, where you overcome the yield stress of the system, then you can even go towards this infinite viscosity or high shear viscosity behavior.
Okay. So still concerning the yield stress in practice, so in industry or in other fields, people have developed various tests, not immediately to determine the yield stress, but finally the result is correlated to the yield stress. This concerns flow test, so people just put some mud, for example, or some paste over a plane, and they look at the final thickness, or there are various other tests like that, penetrometer with a cone or cylinder. You can also look at what occurs on an inclined plane. You can also prepare some drop and look at the size of the drop. So do you think this, why didn't you consider this kind of test? Because finally, with this kind of test, you consider a large volume of material, and then you may avoid some problem you have in the remitters. And do you think, or did people do that already? Or what do you think about that? Do you think this could be developed and maybe correlated to your data?
Yes, actually, not about the inclined plane, but actually I presented in my thesis, there is another method. I think it's quite simple, and it's a type of flow test, and it's a funnel test, that you have a kind of a funnel which is with certain opening, and then because actually I tried that experiments on the vessel, because it's super easy. You don't need any rheometer or anything. You just take the sample out, you put it in that funnel, and then you allow it to flow for a certain time, and then you see how much material comes out. Because if it is too liquid-like, it should come out immediately or within a few seconds. And if it is not liquid-like and if it is strong, that you can say that, okay, maybe it will offer too much resistance to the ship if we are going to sail through it, then you can say it will not come out of the funnel, and then you will immediately see it on the vessel. And that's what I did. And then I tried to correlate it with the fluidic yield stress, or the yield stress value that I got. And then I found a nice correlation that if you are certain, like below that certain value, I think that was around 30 pascals, if you are below that value of this yield stress, you can really see that the material is flowing like really fast. So now you see that's a kind of a bulk material, not in a very small geometry where you have a lot of problems, but it's a bulk material coming out of any geometry. And then you can easily identify that, okay, there is a correlation as well with yield stress. And then you can do that on the ship, I think within a few seconds, and then you can throw the sample back. So that could be another alternative, but I was not able to do too many experiments to find the right correlation with rheological properties. So I think I would suggest in future, I think that could be another solution that even if you have enough data set of rheological properties, and then one option is also in situ rheometer, which is like rheotune. So you can get a correlation with density, and then density can be converted finally into yield stress. That is one option. But the second option is that you can have this funnel on the ship. You just take out the sample, just take the time, and then say, okay, it is very liquid-like till that level. So it is more like a fluid layer. So it should be navigable, and then you can put it back, and then you can have your data out of it. So that could be, I think, another option apart from rheology, which is very simple, very fast, bulk, no small things, no errors, no artifacts, no lot of problems. You don't have to take samples. So I think I would suggest to go maybe in that direction as well.
Okay. Again, in practice, how do you see the possibility to apply your knowledge of the variability of the material behavior depending on the sites where you pick up the material, or depending on the density, or depending on the organic matter? So you have plenty of measurement, as you said.
Yes.
You've done a lot of measurement. So now you see the trends. You see how the material evolved. So you have a big knowledge of all this. So now, do you think this can be used directly to be transferred to some application, or this is something that somebody like you, as an expert, must have, and then can discuss with people in the application? Or so, how do you, or do you think you can make some recommendations, some rules, and send them?
Yeah, I think actually now I just discussed with people from Port of Hamburg, and actually I realized that the correlations that I developed for different locations, like density yield stress correlation, because I think that's the most famous correlation that is typically being used in situ conditions for mud. So I developed this correlation, and then I found this correlation for different locations, and I found that this correlation is actually different for different locations. So that's what we discussed, that now they are going to use this correlation for different locations in their in situ device first, so that they can really go to different locations with different correlations, and then they are going to check the density, and then it will be automatically converted into yield stress values, and then they will collect some samples as well, and then they will validate that the data set that I created, and then they use this equation or this correlation, and they put this correlation in the in situ device, and then they measure some values, but then they validate it again by collecting more samples, and then I think that will be kind of a direct application, that, okay, that the knowledge that I created was first used in situ devices. And the second application, that what I mentioned, that for the CFD simulations, if you are really interested in that, how a ship goes through the mud, then you need rheological parameters for maybe different locations, or maybe you need these correlations as well. So that will be another point as well, that you can use this knowledge. So I think it will be kind of directly applicable, but you cannot decide that what I suggested in this thesis, that okay, 50 Pascal is navigable, but it's not like obvious that okay, 50 Pascal is navigable. You need certain more experiments, like CFD or in situ pilot experiments, and then you see that, okay, ship even can pass through it, can maneuver through it, you can control the ship with these yield stress values. So I think it's still applicable in, I think, most of the ways, but for this particular yield stress value as a nautical bottom criteria, I think a lot of research needs to be done. So I will say that that's need to be, I think, need to be considered by the port authorities. This 50 Pascal value, you can say, is just a kind of a starting point, not the final value.
Okay, so thank you. I am satisfied with the answers.
Thank you for the opposition. Then we now move to Professor van Loosdrecht.
Dank u, meneer de rector. Waarde promovendus, congratulations with the thesis. It's always nice to see how a very practical problem of a ship navigating a river can be translated into really fundamental research questions, and they can also be addressed and maybe translated back, but let's have some discussion about that. One of the aspects you use is a sedimentation experiment from which you then derive the densities of the flux, and that you do in paragraph 4, in chapter 4, paragraph 4.4, and you use in the end Stokes equation, equation 2.7, to calculate the density. Are you really allowed to use that equation, or where are the limits of using that equation?
Yeah, hooggeleerde opponent. Yeah, maybe I could show, I think, the picture that you are referring to is 4.4.
Yeah, it's either equation 2.7 or paragraph 4.4.
Or maybe I think I can just say, because the question is mainly that if we can use that, maybe with this Stokes equation for this settling velocities for this flux, and actually the answer is, it's a bit trade-off, because this equation is mainly for individual particles, while in this case, it's not individual particles, but it's a kind of a combination of particles together with organic matter that is settling down. So I think it's a first trial, you can say, but I would not say that it's the right one, but it was just an idea just to see that if we can find something interesting out of it. But I think it needs to be modified, and I think we have some ideas that, okay, we need to modify it, because for single particle it's perfectly fine, but when we have flock, a combination of particles, then you need to adapt it somehow. I don't know yet, but I think, yes, I agree.
Yeah, there are two things which are probably different. One, it's not a smooth spherical particle, so you will have a drag force in some ways. And the other aspect, which is often discussed in this context, is that during the sedimentation, there's flow through the particle instead of flow around the particle. Now, the drag force, I think that's, everybody will agree, but that last argument, have you been thinking about it, and do you think there's flow through the particle during such a flock which is sedimenting?
Of course, I think because we see the nature of the flocks, and we really see that these are like really fluffy and open structure, so you can really expect that the flow can...
Would there be enough pressure difference over the flock to drive flow through the pores of the flocks?
I think it depends on the flock structure or how much it is open. So I think it's a bit dependent on the type of flocks, but I think it's...
Yeah, no, it's logical that that you have to make simplifications, but this effectively means that you somehow, I think, underestimate the density, if I'm correct. How would that influence your further conclusions you derive from the density measurement? Is there the influence on the further...
Actually, I think in this thesis, what I did, actually, I tried to correlate with the size of the flocks, or maybe the structure of the flocks, with the rheology, or rheological properties, or the yield strength, or modulus. So I actually did not use the settling velocities to correlate with rheology. So luckily, I'm safe in this case, because I was not using too much the settling velocities, because this research was done.
You use the density. You use the settling velocities to get the density.
Yes, but I did not use the density as well, because the idea was just to see if the flocks are bigger, or if there is organic matter or large amount of organic matter, it will create bigger flocks. And then maybe it can somehow correlate it to yield stress or rheological properties, and found, oh yeah, there is a correlation.
Good,
so I thought, okay, whatever happens with the settling velocity, let's ignore this.
Let's then discuss that organic matter part. You have done interesting experiments to see if you degrade the organic matter, if that's disappearing. Maybe first you claim that the organic matter is a flocculant, might operate as a flocculant for the particles or bind the particles together. That's, I think, that also a very common agreed aspect. But part of these biopolymers, which you are degrading, they also have a very high water binding aspect, which would mean that you get also a quite high amount of fixed water. And by removing that water binding polymer, you also remove a lot of fixed water in the flocks. Now, I have no idea how that influences further your rheological measurements, but would that influence if you would have, say, super adsorbers in your flocks which are then degraded?
Yeah, I think for what we did in our analysis, the idea was just to see how this degradation is actually affecting. So we found out that, okay, there is some degradation, we produce a lot of gases. So I think something is degrading. So the biopolymers is gone, or part of it is gone, not all of them.
No, that's fine.
And then it decreases yield stress a lot. But I think what you are talking about, if I think now, because we didn't consider that fact, because it's so kind of a small part of my research, so I didn't focus that much on that thing, that, okay, maybe a lot of other phenomena is occurring, but I suspect that maybe it should affect, I guess. In which way, we can discuss.
Well, maybe some future research.
Yes, that's a nice idea.
But what for me was a bit surprising is to see that the aerobic degradation, had much less impact on the flock behavior or the rheological behavior than the anaerobic degradation. Now, usually the aerobic degradation is way more efficient in removing organic carbon. What's behind this?
Yes, actually, that's what I think. First, when we saw the results, we were expecting something like that, okay, aerobic will degrade everything, and we will have even more degradation, and the yield stress will be even more weaker. But when I saw these results, so first I thought maybe there is some experimental error, or maybe I didn't measure correctly, but then we repeated with so many samples, and then we figured it out that, okay, it is getting higher and higher with some samples. But then what we thought, that in your natural samples, it's typically in anaerobic conditions. But when you take out your sample and put it in aerobic conditions, then in those samples you have some metallic ions, which are in, I think, adsorbed condition in anaerobic state. But when you allow it to oxygen to enter, then these metallic ions can liberate it from the samples and then can start to interact with the clay or with themselves and can form interesting structures with the clay or also metal complexes. So what we thought that maybe there is something going on
My
from this
question
side.
was a bit going in that direction because you will have likely sulfites in the sediment or maybe even sulfate in the water you add, and which might lead that there's more sulfites in the anaerobic condition than aerobic, and your iron is in the oxidized form rather than the reduced form. Now,
Yes.
I'm not sure if you have been looking to the iron and the sulfites, or if you can, from your general rheological knowledge, infer what might happen.
Yeah, I think that was the thing, because when we saw these results, so I think that was the first thing that we saw, that, okay, how much iron content we have. And I think for particular locations, we see that, okay, there is iron content, and maybe that is creating this kind of large increase in the system. So I think, but at that point, we were not so sure. So I think there is a lot of room, I think, it's still there to really understand what is going on with aerobic. Maybe it's metallic ions, or maybe something else.
Okay, thank you. Bedankt, meneer de rector.
Thank you for the opposition. Then I would now like to invite Dr. Kiricek to continue the discussion.
Dank u wel, meneer director. Meneer director, I have a question about proposition number 2.
Waarde promovendus, could you ask one of your paranympha to read proposition number 3?
Yeah, can you please read proposition number 2, please?
Two-step yielding occurs due to the shear induced structure reorganization of blocks in parallel to possible wall-slip article.
Waarde promovendus, I have a question about this proposition. During your research, I think we discussed a lot the dual yielding or two-step yielding and also the wall-slip artifact. And I was wondering, can you really distinguish from your measurements whether it's wall-slip effect or it's dual yielding?
Zeer geleerde promoter. Yes, during my research, actually, we had a lot of discussions on this thing, that if it is really a two-step yielding or like a system behavior, or if it is coming from experimental artifact, which is quite common in these kind of systems, which is wall slip. So initially, I was a bit confused as well, but then there are some approaches available in the literature that either you can vary the gap between the plates and you can identify if there is a significant wall slip, you can easily identify from it, or you can use different geometries or roughened geometries. You can, the surface of the geometry, you can make it more rougher so that the wall or the material at the wall will not slip. And then you can avoid it, and then you can compare the results with smooth geometries and roughened geometries. So I did that as well, and I find that, okay, the results are more comparable. And also the one fact that was making me like think again and again, that if you have a really liquid-like sample, I was a bit doubting that how you can have wall slip. Because yes, if you go to higher densities, then maybe you can have maybe wall slip together with other phenomenon. But with very liquid-like samples, I was a bit confused that maybe there is something going on in the system. So that's what triggers me that, okay, maybe we could analyze maybe in this optical thing where you can really shear the material and then you can see what is happening with the structure. So that's why we did this rheoptic measurements, and then we try to correlate it with the rheological measurements. And then we actually kind of figure it out that, okay, there is a kind of change in structure from very connected network to an interesting structure, which is like a cylinder, like rolls, and then these rolls are broken down. So what I would say to make it to make this discussion as a conclusion, that either you can have a combination of wall slip plus this reorganization. So what you can do, if you can use a very rough geometry, or if you do not allow it, or by using certain protocols, if you do not allow it, this combination to happen, then you will not have maybe two-step yielding, or maybe it's only reorganization, and then you can only avoid it by using certain protocols or geometry. So either it's a combination of both, or it's reorganization, I would say, from my research.
But how can you check if it's combination? Can you think of rheological experiment that could clearly give you an answer that this wall slip effect occurs in parallel with dual yielding, and it's really easy to distinguish between these two processes at low shear rates?
I think this is a bit tricky, I guess, because the thing is, when you try to avoid one thing, and with the same phenomena or with the same thing that you're trying to avoid it, the second thing will also be avoided. Because if you are going to use very rough geometries with grooves, let's say, or with bigger, I think, on the corrugations on it, you will avoid, obviously, the wall slip, but you will not allow the sample to restructure as well. Because in that small gap, you have these grooves, which will disrupt the structure a lot. So you will not allow these smooth surfaces to make this nice cylinder-like structures. So I think if you try to avoid one, I think you will avoid both. So if you really do not want to see this, just go ahead with these very rough and very corrugated things, and then you will have a one-step yielding, and then you can use it. But that yield point will be very comparable to the fluidic yield stress. So the knowledge that I created in this thesis, like for fluidic yield stress, or the knowledge that I presented that, okay, fluidic yield stress can be used. So I think that knowledge will still be applicable, but maybe the static one may be gone. So that could be the conclusion out of it. That's what I would say.
Okay, but if we are still interested to measure also at low shear rates, would your protocol will be applicable for these measurements, or you need to think about other type of protocols?
I think for what I found during my analysis, I think it was okay that even if you apply, because you can start from, you can really apply low shear stresses, and then the shear rates are actually quite small, and then the material will, or the geometry will not move, and then it will start to move, so you can even go from very, very low shears to high shear as you want. So I think with this protocol, I think you can easily tackle this problem, but I think so.
All right. Mania Director, do you have time for a small question?
Yeah, there's still time for a question.
Okay, excellent. Thank you, Mania Director. I think one of the conclusions of your thesis was selection of 50 Pascal as a nautical criteria. I was wondering why 50 Pascal? What is it based on? So can you elaborate on this a little bit?
So actually, I think the first point where I thought that, okay, 50 Pascal could be the starting point, because in Port of Emden, they are already using this yield stress as a nautical bottom criterion, and they are using 50 Pascal as a criteria. So I thought, okay, that could be the starting point, because we already observed in literature that someone is using that, but it's just a starting point. I'm not saying that it is navigable here as well for Port of Hamburg, but then I thought, okay, and then I also correlated with this structural recovery, and I observed that, okay, with 50 Pascals or below 50 Pascals, your structural recovery is quite fast, so which also shows that your system is quite weak. So that also hints towards that, okay, maybe 50 Pascal is a good starting point. Apart from literature value, thixotropy, or the structural recovery also tells you nice information. So then I thought, okay, let's start with 50 Pascal, and I think now they are using for berthing, but I think in future, I think they can even go to a bit lower values, because maybe 50 Pascal is a bit higher or a bit on the higher side. So I think they can even go to 20 Pascal or 30 Pascal. That's what I found from this funnel test, because where everything flows, so it was really liquid-like. So I would suggest that maybe 20 or 30 Pascal would be a nice starting point for navigability or sailing through fluid mud, while 50 Pascal is good for maybe berthing or some other things, I don't know.
But why 20 Pascal? Based on what?
Based on this funnel test, because for funnel test, I found this volumetric flow rate, or I found that, okay, within 2 minutes, how much material came out. And then I realized that, okay, within 20 Pascals or in 30 Pascals, all the material came out of the funnel in very short time, so which shows that actually it was very, very liquid-like. That's how it came out of the funnel. And then I thought, okay, maybe this 2 or 20 or 30 Pascal is the limit where material is so liquid-like that even bulk can flow out. And that could be the value where even ship can pass through it, because it's really liquid-like. So that's the idea where I thought, okay, maybe for navigability through fluid mud, maybe 30 Pascal or 20 Pascal would be a better option instead of 50 Pascals.
You're
but
referring,
that's still...
you're referring to the figure
yes.
8.4, right?
Yes, yes.
Because on 8.4 figure, I see a clear difference between 40 Pascal, right? Not 20 or 35,
yes.
but not 20.
Yes, but this is actually quite less number of data points. So I cannot say that if it is really 35, that's why I thought, okay, let's put it slightly lower for the safety margin. But I think if you really want to make this correlation, I would really suggest, but I think I already suggested that maybe they could do some more experiments because it's very easy to perform. You just have this small device, you take the sample out, you put it in the funnel, just take the volume, throw it back. That's it. You don't need to take it anywhere, and then you can further verify maybe 30 Pascal or even 35 or maybe 20. So I think this range should work somewhere.
Does the opening of the funnel influence this measurement?
Oh yes, because I think I used the bigger one that I found, because the problem was that if you have too many bigger things, chunks, because when you take the mud out of the sediment bed, sometimes you have like snails or I don't know, seashells, or I think a lot of things you can find in that, and if you put it directly, and if you have a very small opening, nothing will come out, even if you wait it for 2 hours. So that's how I thought, okay, maybe we should use a bigger one, at least, but not too big, because otherwise everything will fall down ultimately. So you need to select from the available options slightly bigger one so that you can avoid this lump formation or these strange things to clog your system. So that's what I thought.
Okay, so that will be a follow-up of your project, right?
Exactly.
Okay.
Are you satisfied with the answers?
Mania Director, I'm satisfied with the answers.
Okay, thank you for the opposition. Then we now move to the promoter, Professor Pieter Zak.
I'd like to start by saying, thank you. It's very nice to see this large body of work spanning many disciplines, in fact. Typically in Delft, we like to make practical tools, we like to make numerical models, and you've talked about CFD models. Could you say something a little bit more about how you plan to translate your work into these CFD models and what the limitations would be, the advantages versus limitations?
Mm-hmm. Yeah, okay, the promoter. Yeah, I think that is kindly, yeah, I think it is bit out of the scope of this research, but I can try to correlate something, because I know a person sitting there. I was working with him because he's a kind of a CFD simulation guy. Mm-hmm. So what we discussed together that, okay, which rheological protocol and which rheological method and which rheological or yield stress values or infinite viscosities that we can use. So I learned from him that, okay, we need this actually rheological input for him, and then he was using CFD, or he was performing CFD simulations. I think now he did for the plate, moving through the mud, and then he experienced this resistance offered by the mud to the plate, and then he was converting into, and then he was using CFD simulations by using rheological parameters that I measured. And then it was actually quite a nice study where we correlate these rheological measurements with the CFD simulations that he used, and I think there is still work going on, because that was just for the plate. But now I think the next step will be to use maybe a small ship, or maybe to use it in situ conditions, to have a ship and then try to simulate it by using rheological data that I provided and CFD simulation. So I think that's what I understand so far from discussion with him. I think that's what I can say about it.
Director, may I ask about proposition number, my glasses on, 9?
9?
Please.
Waar de promovendus, your paranympha, have a very busy afternoon, I would like to ask you whether you would ask your paranymph to read proposition number 9.
Okay. Can you please read proposition number 9, please?
Find the PhD position in Delft is much easier than to find an accommodation in Delft.
Mm-hmm.
Would you like to?
Yeah, actually, I think maybe not a lot of Dutch people will like it, but I think maybe they know the condition as well, because finding accommodation here, because when I came here initially, I thought, okay, it would not be that much difficult because I got this PhD position, because I would discuss that, okay, how I got PhD position and how I got this accommodation, because then you can really see which is more difficult. So I think I gave this interview for this PhD position, and I think within within few days or maybe even, I think 2 or 3 days, I got the email that, okay, I got selected. So after one interview, it was enough. So I thought, okay, that's easy, because my degree was directly relevant to this project, so it makes sense as well. But then I came here, and I think I found a temporary accommodation that was available for 3 months, I guess. So I thought, okay, 3 months is more than enough to find a nice accommodation. So I started living there, and then I started to hunt in Delft, because I thought it's better to live Delft. And after 3 months, I was like visiting places, like you have to go there and we'll take interview. Okay, what are you doing here? And after I said, okay, sorry, we selected some other person. And then I remember I went to one position for viewing, and I just mentioned to them this proposition. I said, yeah, now I realize that PhD position was getting like very easy to get, and now it's really difficult to find accommodation. And they were laughing a lot. I said, okay, this is now my proposition. And I think after 3 months, I was not able to find accommodation in Delft, so I was living in Schiedam, which is also not far. And after 1 year, luckily, I think my wife was coming, so we thought, now we need to move to Delft. And I think maybe due to luck of my wife, I was able to get accommodation. So maybe it's luck there as well.
Thank you. I'm satisfied with the answer.
Thank you for the opposition. And we still have a bit of time for the other promoter, Dr. Shakeel.
Thank you very much, meneer de rector. Well, to conclude this nice session, I think I will also ask a question about the proposition. And let's go to proposition number 10 then, the last one.
Waarde promovendus, could you ask your paranymph again to read the proposition? In this case, it's proposition number 10.
Okay. Can you please read proposition number 10, please?
It is rather surprising that there is no motivation to learn Dutch during one's PhD, whereas there is an obligation to write a PhD thesis summary in the language.
And I would like to connect this to proposition number 9. Don't you think that if you would have been speaking Dutch, it would have been easier to find an accommodation in the Netherlands?
That's, yeah, actually, sorry. What was that? Zeer geachte promoter? Yeah, actually, that's what I thought as well. But actually, most of the viewings that I did for the accommodation, those were international students. So they were not speaking Dutch, and I think most of them were not Dutch as well. So that's why even more frustrated for me that, okay, I'm also international, so you're also international, so I think they will prefer me. But I think I did not have very good social interaction with the people, so I think they realized even in one meeting. And then I think it was not related to Dutch, but I think it was related to something else. I don't know.
Okay,
maybe luck or
do you
appearance.
think it's important to learn Dutch when you're living in the Netherlands?
I think if there should be a motivation that if you cannot survive without Dutch, then I think at some point you will be forced automatically that, okay, if you are going to survive in this society, you need Dutch. Like, now I recently moved to Germany and realized that if you really want to survive in Germany, you cannot survive without German. So that's the motivation. But here, everyone speaks Dutch, English, and I didn't find any motivation to learn that, so I said, okay.
Do you have a recommendation for the Dutch people in the room? Like
they don't speak English.
Exactly.
Yeah, maybe other people will not like it, but please speak English.
But rather than that, something else maybe that you would have liked to learn about the Dutch culture that is accessible or not with the language?
I think in every culture, if you learn the language, I think the people will become more open. That's, I think, obvious, I think, in any case, because then you can connect with the people, because if you are speaking their language, they will prefer to discuss maybe other things which is related to culture as well. But if you are not learning their language, maybe they will feel that maybe you are not interested in their culture as well, because I think language is an important part of culture as well.
I completely agree, but were you interested in Dutch culture?
I think at some point, yes, but actually I am very poor in learning languages. I don't know why. I'm really afraid that I cannot learn, I think, 2-3 sentences even in Dutch. Even these words were, I think I didn't prepare too much for my defense, and I prepared more for these words so that I will not pronounce it wrong. I did not, if I do it wrong or not. So I think it's important, but for me, it's difficult. And now I'm also thinking that how I'm going to learn German. I will come back.
I must add to that if you would have learned Dutch, learning German would have been easier.
Yes. That would be that's a nice point.
Oh, I think I would like to ask something else, but I have...
Thank you, Madam Beadle. I request the promovendus and the paranymph to go back to the seat. The committee will withdraw now for further deliberation. The session is adjourned. Princess and the Paranymph to stand in front of the committee. Het College voor Promoties van de Technische Universiteit Delft, vertegenwoordigd door de hier aanwezige commissie, heeft u, na kennis te hebben genomen van uw proefschrift met stellingen en na uw verdediging daarvan te hebben gehoord, met achtneming van het bepaalde in de wet op het hoger onderwijs en wetenschappelijk onderzoek, besloten u de graad te verlenen van dokter en wel cum laude. Ik verzoek de promotor door het college van promoties als zodanig aangewezen zich wel van de haar opgedragen taak te kwijten.
Uit kracht van de bevoegdheid bij wet toegekend aan het college voor promotie, verklaar ik namens dat college, hier vertegenwoordigd door de rector magnificus en de overige leden van de commissie, bij deze u, Ahmad Shakeel, te bevorderen tot dokter en wel cum laude, en u alle rechten te verlenen welke aan deze dokterstitel zijn verbonden. Ten bewijze hiervan overhandig ik u het diploma dat u recht geeft de titel dokter te voeren. Ondertekend door de rector magnificus en de promotoren en voorzien van het zegel van de Technische Universiteit Delft. I think the film is finished. Try to look mature.
It's the co-promoter's privilege to be the first to congratulate the young doctor. Dr. Kiricek, the floor is yours.
Thank you, meneer director. Dear Dr. Shakeel, dear Ahmad, it is my pleasure and honor to stand here in front of you and give the final speech during your PhD defense ceremony, especially since you expected Claire to give the final speech. But as you surely learned during your PhD lifetime, the academic world is cruel and full of surprises. And I can assure you that more surprises are waiting for you starting this evening, so be prepared. Talking about surprises, personally I can recall at least 3 times when it was your turn to surprise, or should I say impress, your supervisors. The first time was during our first monitoring campaign, conducted together with Hamburg Port Authority in Hamburg. After you accepted the PhD position, we got you nearly straight from the plane from Pakistan to the surveying vessel. You were totally unprepared, wearing a thin summer jacket, and looked apprehensive. The people from Hamburg Port Authority lent you a spare waterproof overall, gloves, and helmet so you could participate in the sampling campaign. Putting on the equipment was already a challenge, as you never wore those things before. But that was a change. What was a change in 1 year? You learned very quickly the monitoring routine, you ignored the weather changes occurring several times during the day, and in fact you became the coordinator of the field surveys. You told everyone on the vessel what to do and when, while filling in the log journals. I'm pretty sure, in case you want, that Nino will be happy to offer you a job on his surveying vessel. The second time you managed to shock Claire and myself was on the 6th of May 2021. That day, we received 3 emails from scientific journal editors informing us that the papers submitted by Ahmad Shakeel were accepted. 3 papers were accepted within 1 day. What a record. I guess this record would be hard to beat, Ahmad. The third surprise is related to your publication records as well. As it is shown at the end of your PhD thesis, you clearly mastered the art of publishing papers in peer-reviewed scientific journals. However, unlike many people, you managed to publish papers within two parallel research lines. The first research line being on rheology of mud, the main research line of your PhD thesis, and the second research line being on rheology of polymers, which is the follow-up of your master study. And you not just published a few papers, you published 9 papers and 2 book chapters on this topic. I think it is more than enough for another PhD thesis, or 2. For your PhD, you conducted a huge series of systematic studies on the rheology of natural mud. The outcome of your research will serve as the input parameters for large-scale CFD studies, which model the maneuverability of ships in fluid mud. The limit of 50 Pascal that you found based on the huge data set you acquired, and it will serve as a threshold for berthing in pilots' experiments in Port of Hamburg. And the rheological protocols you developed are currently used for other projects, particularly projects of Port of Hamden. Since April, you started your postdoc at the University of Freiburg, and I, and of course Claire, wish you all the best in your new scientific journey. We all hope, of course, that we will continue to collaborate one way or another, as we have still many interests in common. But for today, let us just be proud of your achievements. Congratulations to you and your family.
Learned Dr. Shakeel. You now have the right to use the title of doctor. Your doctorate means that society can rely on you, rely on your judgment, and that you will act transparently and communicate independently about your result and the societal relevance of your work. In other words, your doctorate implies that you will uphold scientific integrity. I wish you a great deal of wisdom and prosperity with your new degree. On behalf of the Board of Doctorate of Delft University of Technology, I congratulate you on your doctoral degree. Dr. Shakeel, you can now return to your seat together with your 2 paranympha. Ladies and gentlemen, I thank you for your presence. Hereby close this academic session.